Welcome to our series on organic reaction mechanisms. In this video, we are exploring one of the most powerful and elegant transformations in synthetic organic chemistry, the Diels-Alder reaction. This reaction is classified as a 4+2 cycloaddition, where a conjugated system of 4 pi electrons, the diene, reacts with a system of 2 pi electrons, the dienophile, or diene lover. This single transformation allows chemists to construct complex, six-membered rings with remarkable stereocontrol. To understand the core of this reaction, let's look at a classic example: the reaction between 1,3-butadiene and propenyl, also known as acrolein. Unlike simple ethane, propenyl is a highly reactive dienophile. Under relatively mild thermal conditions, these two molecules reorganize their electrons to form a cyclic structure. In this process, 2 pi bonds are consumed to form 2 new carbon-carbon sigma bonds and 1 new pi bond. The resulting product is a 6-membered ring containing a new double bond, with the aldehyde group from the propenyl retained intact on the ring. Before the reaction can take place, we must consider the conformation of the diene. 1,3-butadiene exists in an equilibrium between the S-trans and S-cis forms. While the S-trans conformation is more stable due to reduced steric hindrance, it is effectively unreactive in a Diels-Alder reaction. In the S-trans state, the terminal carbons are too far apart to reach the dienophile simultaneously. Therefore, the diene must rotate around its central sigma bond to adopt the S-cis conformation, bringing the p orbitals into the correct alignment for ring closure. A single concerted step, the concerted 4+2 cycloaddition. The Diels-Alder reaction is a concerted and pericyclic process. This means that all bond-breaking and bond-forming events occur simultaneously in a single step through a cyclic transition state, without the formation of any charged intermediates. As the diene and propenyl approach each other, 6 pi electrons move in a continuous, synchronized loop. 2 pi electrons from the double bond of propenyl move to form a new sigma bond with C1 of the diene. The pi electrons of the diene shift from the C1-C2 position to form a new pi bond between C2 and C3. The remaining pi electrons from the C3-C4 position move to form a second new sigma bond with the other carbon of the propenyl double bond. This electronic dance replaces 2 weaker pi bonds with 2 stronger sigma bonds, which serves as a major thermodynamic driving force for the reaction. The reaction yields a new 6-membered ring, preserving the original aldehyde group while forming 2 new sigma bonds. The Diels-Alder reaction is significantly accelerated when the dienophile is electron poor. Propenyl is an excellent example because it contains a strong electron-withdrawing aldehyde group. Other common electron-withdrawing substituents include nitriles, esters, and nitro groups. For instance, acrylonitrile is an activated dienophile due to the strongly electron-withdrawing nitrile group. Similarly, nitroethylene is highly reactive because of the powerful electron-withdrawing effect of the nitro group. Ester-substituted dienophiles, such as methylacrylate and dimethylmalate, are also classic examples commonly used in Diels-Alder reactions. The Diels-Alder reaction is stereospecific, meaning the stereochemistry of the starting materials is perfectly preserved. If you start with a cis dienophile, like dimethylmalate, the substituents will remain cis to each other in the product. If you start with a trans dienophile, like dimethylfumarate, they will remain trans. Because the reaction is concerted, there is no time for bond rotation to occur during the process. When both the diene and the dienophile are unsymmetrically substituted, we must predict the regioselectivity of the reaction. Let's start by comparing how different substituents influence electron flow through resonance. By analyzing these resonance contributors, we can identify the partial charges across the pi systems. This reveals which carbons are electron-rich and which are electron-deficient, setting the stage for the reaction. It all comes down to electronic matching. To find the lowest energy pathway through the transition state, the delta- site of the diene naturally aligns with the delta+ site of the dienophile, negative to positive, much like a magnet. For one substituted dienes, such as 1-methoxy, 1,3-butadiene, this interaction leads to an ortho-like product. As shown here, the electronic matching places the two substituents on adjacent carbons. In contrast, for two substituted dienes, such as our 2-cyano example, the same logic applies. The nitrile group withdraws electron density through resonance, polarizing the system so that the terminal carbon aligns with the electrophilic site of the dienophile. This results in a para-like product, giving a clear 1-4 relationship between the substituents. When using cyclic dienes like cyclopentadiene, the substituent on the dienophile can be oriented in two ways, endo or exo. In the endo transition state, the substituent, such as the aldehyde group in propanol, points toward the newly formed double bond of the cyclopentadiene ring, whereas in the exo transition state, it points away. To allow this interaction to occur effectively, propanol adopts a favorable 𝒔-cis-like alignment, which orients its carbonyl pi system toward the diene framework. At this stage, two distinct types of orbital interactions can be identified. The primary orbital overlap occurs between the terminal pi orbitals of the diene and the pi star orbital of the dienophiles CC double bond, leading to the formation of the two new sigma bonds. In contrast, the specific 𝒔-cis-like alignment of propanol enables an additional secondary orbital overlap. This secondary interaction occurs between the filled pi orbitals of the diene, C2 to C3, and the empty pi star orbital of the carbonyl group on the dienophile. This interaction provides additional kinetic stabilization to the endo transition state, making the endo product the major product in most cases, a phenomenon widely known as the endo rule. Finally, it is important to remember that the Diels-Alder reaction is inherently reversible. While we often focus on the forward synthetic transformation, many Diels-Alder adducts can, in principle, undergo a retro-Diels-Alder reaction under the appropriate conditions. At high temperatures, the entropy term T delta S becomes the dominant factor in the Gibbs free energy equation. Because the retro reaction breaks one molecule into two, it is entropically favored, shifting the equilibrium back toward the starting materials. Let's review the essential points of the Diels-Alder reaction. 4+2 cycloaddition. This is a concerted, one-step process where 6 pi electrons, 4 from the diene and 2 from the dienophile, shift simultaneously to form a new 6-membered ring. 𝒔-cis conformation. The diene must adopt an 𝒔-cis conformation for its orbitals to align correctly with the dienophile, allowing the reaction to proceed. Stereospecificity and endo rule. The reaction is stereospecific, preserving the original geometry of the reactants. In most cases, it prefers the endo orientation because secondary orbital overlap provides additional kinetic stabilization. Retro-Diels-Alder reaction. The process is inherently reversible. At high temperatures, the entropy term T delta S becomes dominant, favoring the retro-Diels-Alder reaction, which breaks the adduct back into its starting materials. To wrap up, Those who wish to deepen their understanding of the Diels-Alder reaction are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.